Right. Good morning, everyone.
Good morning, sir.
Good morning, sir.
Good morning, sir.
Morning. Good morning. Good
Good
morning.
morning, sir.
Good morning. All right. So today we're going to deal with strings or ropes which have got mass. I've got rope based on frictionless horizontal surface. Okay. Here is a rope whose mass is m, length is l. So mass per unit length, which is given by lambda, represented by lambda, is m by l. So mass per unit length is lambda. So if I take unit length, let's say this length L, if I take unit length, its mass is going to be m by L into 1. If I take 2 units, how much is the mass be? M by N into 2. Alright, length times lambda will give me mass because that's this is called linear mass density. Alright, so linear mass density is given by represented by lambda, which is mass per unit length m by L. Alright, now there is some force F naught applied over here. Required to find acceleration and tension at a distance x from this point. And graph it. All right. So first is acceleration. How do I find the acceleration? Net external force by total mass. What is the net external force on this whole rope? F naught. So acceleration is F naught by m. Fine. All right. Now required to find the tension at a distance at a point which is at a distance x from this end, from the end where the F naught is applied. So what I do, I'll break this string into two and I'll draw the FBD. As I told you, if you draw the FBD correctly and write F is equal to MA, you're done with the problem. This is F naught. This length is X. This length will be L minus X, L naught minus X. Tension at this point will be T in this direction. Tension at over here will be T in this direction. Reaction of that is on this string. There is action reaction. Action reaction pair is along same line of action and they'll be equal in magnitude and opposite in direction. Right. So this is the scenario. And normal reaction will have counterbalance by mg. Normal reaction will have counterbalance by mg. I'm not considering that because my motion is along horizontal direction and vertical motion is, there's no motion in the vertical direction. It's in equilibrium in vertical direction. So normal reaction is counterbalanced by mg. Here also normal reaction is counterbalanced by mg. So there is a net force along horizontal direction. So I know the acceleration of the two particles, a naught and a naught. So MAD is also done, FBD is also done. All I have to do is F is equal to MA. So I'll write, I want to find tension in the string. See, I can either use this one or this one, but I'll use this one because I've got only T is equal to F is T is equal to M into A. So T is equal to mass into acceleration. But what is mass of length? Mass of length L is M. So mass of length L minus X would be lambda into L minus X. This is mass into acceleration A. So T is equal to lambda into L minus X into A, which is F naught by M, which is lambda into L. So lambda gets cancelled out. I'll have F naught into 1 minus X by L naught is my tension in the string as a function of X. Do you all get this? Simple math. This is the physics. Physics is done till here. Tension is equal to mass into acceleration. Mass times acceleration is I found it to be F by M, where M is lambda into L, right? M is lambda into L. And the mass of this string is lambda times length, because linear mass density into length will give me mass of this part. So lambda times L minus x is into F by M. M is lambda into L. Lambda gets cancelled out. F naught into L naught minus x by L naught. 1 minus x by L is the tension. Tension in the string. If I plot this tension as a function of x, I get a linear function. At x is equal to 0, the tension is F naught, right? Because at this point, tension is going to be F naught. At L is x is equal to L naught, my tension is 0. Tension is 0 over here. And it's linearly varying. F naught, so y is equal to mx plus c చూస్తే negative slope with shift of F naught. Slope ఎంత ఉంది? F naught by L naught. Negative F naught by L naught. So this is how it will vary. Tension will vary as a function of x like this. When lambda is constant, lambda is m by L, is constant. Linear mass density is constant. It's a uniform row. Any doubts over here, students? Because we're going to complicate this problem with variation of lambda. So any doubt here? Lambda is constant in this problem. Next, we'll take lambda is going to be varying with x. So any doubt over here? It's a uniform row in this case.
Sir,
Yes?
once again, can you see?
Yeah. See, there's a rope. Force F naught is applied on it. Required to find tension at a distance x from this end. All right, from this end, from the end where the force is applied. So what I do at a distance x, I section it. I section the rope and draw the FBD. So this is x, this is lambda, L naught minus x. So mass of this will be lambda into L naught minus x. Mass of this will be lambda into x. FBD would be F naught, T over here, and T over here, and nothing over here. And MAD would be, masses I've written, acceleration is towards right, acceleration of both the parts is same, A naught towards right. And A naught we have already found out. How did we find A naught? Net external force by total mass. Net external force is F naught, by total mass is M. F naught by M is my acceleration. Required to find tension. So I'll use this part and write F is equal to MA. See, FBD, MAD, and then F is equal to MA. So what is F is equal to MA now? Tension is equal to mass times acceleration. What is the mass of this part? Lambda into L minus x into acceleration. What is acceleration? If not by m. But m I write in terms of lambda again. Lambda into L naught. Lambda gets cancelled out. I'll have F naught into 1 minus x by L, which is y is equal to mx plus phi form, which is a straight line like this. So at a distance x, here is how the tension varies. When x is equal to 0, my tension is F naught. When x is equal to L, my tension is 0, and linearly varies between these 2 points. Is it clear?
Yes, sir. Thank
No problem. All right. Now, what should we do now is, I'll give you lambda. Lambda of x is varying as lambda naught into e power minus x by L naught. All right. It varies as e power minus x by L naught. Lambda naught into e power minus x by L naught. So it's a non-uniform row. Look at this. Lambda itself is varying with x. That means it's thicker here. If I see the plot, it's thicker here. As I go away from this point, it gets thinner and thinner. So density is varying. Question is again the same. Find the tension and find the acceleration first, and then find the tension at a distance x from the end. From the end where force is applied. So let's find the acceleration first. Is the question clear, students? Lambda is varying as lambda naught into e power minus x by L. So lambda is varying like this. Initially, it's lambda naught. It's varying like this with x. All right. Now that means it's thicker at x is equal to 0. X is measured from this end, from the end where the force is applied. Thicker at this end. As I go away from x, it's getting thinner and thinner. All right. Please mute yourselves. Okay. Now, the acceleration is again f by m, if not by m. But how do I find m? M is not given to us. Length L is given, but m is not given. Lambda is given, length is given, m is not given. How do I find m? If lambda were constant, I would have written lambda into L naught. That would be the mass. But here lambda is not constant. So what I do, I integrate. I chop this whole of this rope into infinite number of infinitesimal pieces. All right. I chop this into infinite number of infinitesimal pieces. So at a distance x, if I consider uh, just be like this. So at a distance of tau, I consider a small element of width length d tau. All right. Because I'm already using a variable x for this one, I'm not using x again. I'm using another variable tau. So tau is also a distance from this end. All right. I could use any other variable, but I'm using tau. Usually it is used, tau is used, so I'm using tau. Tau is just another variable. Don't be afraid looking at the Greek letter. It is just a simple letter. All right. I could use y. If it's vertical, I would have used y, but I'm using it tau because it's just another letter. All right. So tau is instead of x, I cannot use x because x is already used for to represent a point where I need to find the tension. So tau is the distance from this end of a point of a element which is of width d tau. What is the mass of this d tau? Lambda of x, lambda of tau, d tau is dm. Understand this procedure very carefully, students, because this is the first time we are integrating, we are applying integration to NLM. All right, basic math you are now applying for the first time. So I'll go slow, but be careful. Be attentive and just follow the procedure carefully. Or it's just a procedure. You know, if you are just strategic, you'll be able to apply this to any situation. So dm, mass of this element, which is small m, a small infinitesimal element, is dm. So dm is equal to lambda into dx or d tau. What is lambda? I get it as lambda naught into e power minus tau by L naught into d tau. I integrate this from, I need to find the total mass. That means I have to find from here to here. If I integrate only from here to here, I'll get the mass of this one. If I integrate from here to x, I'll get mass of this part x, of length x. But I want total mass. So I need to integrate this from 0 to L naught. Do you all agree? Who are here? Hasini, Gayatri, Shivani, Bhavna.
Yes, sir.
All right. Let us integrate this. I'll get the total mass. And acceleration would be F naught by this total mass. So F naught by this is going to be my acceleration. not by total mass. So what is all? If I integrate this one, I'm done. So let's integrate it. It's just mathematical, students. The only point we have to consider is I'm sectioning this rope into infinite number of infinitesimal pieces. Of this infinitesimal piece, I write the mass as dm. That dm is lambda tau into d tau, because linear mass density into length. I'm considering the linear mass density to be constant in this width. That's why I'm multiplying with lambda into dx or d tau. Lambda into length is my mass. So lambda is to be considered constant along this region. It's so small, so small. I chopped it into infinitesimal number of. It's an infinitesimal piece, so it is so small that I can consider lambda to be constant in that region. Lambda into length will give me mass of that region, but I get infinitesimal mass. When I integrate this from 0 to L, I get total mass. All right, now let's integrate. So I'll have f naught by lambda is constant. It comes out integral e power minus x by L d tau, e power minus tau by L naught by d tau from 0 to L is my integral. Look at this. What is integral a power x dx? It is a power x by a. All right, if I differentiate this, I should get this. How do I differentiate this? E power ax into a by a. A gets cancelled out, I'll get e power x. If I differentiate this function, I should get this function, inner function, integrand. So integral of this would be this one. I'm just rechecking. Integral of this is e power ax is e power x by a. I'm just confirming that if I differentiate this, what do I get? E power x into a by a. A gets cancelled out. E power x is what I'm getting back. The integrand I'm getting back the integrand. All right. Now, same thing over here. What is integral e power minus tau by L naught? E power minus tau by L naught. E tau is equal to 0 to L naught. So lambda times e power minus tau by L naught by minus 1 by L naught. Under the limit 0 to L naught. So what I now get is lambda naught into L naught. I invert the limits because I want a negative sign here. So e power minus tau by L naught from limits L naught to 0. All right. I've inverted the limits. Why? I've removed this negative sign over here and inverted the limits. So I substitute 0 first. What I get is lambda naught into L naught into 1 minus 1 by E is the total mass. You all agree with this? Is it okay? Just check. I could be wrong in this one. Just check this step from here to here. Is it correct? Is what I've written correct? From here to here, is it correct? I've substituted the upper limit 0. E power 0 is 1. I got it as 1. I substituted L naught. E power minus L naught by L naught is e power minus 1. E power minus 1 is nothing but 1 by E. All right. I got the total mass. So acceleration is F naught by lambda naught into L naught into E minus 1 by E. This is my acceleration. Is it okay? It's just math. Physics was only F by M. Rest is math. To get M, what did I do? I integrated it. I've chopped this into infinite number of infinitesimal pieces. I've written the mass of an infinitesimal piece, dm. I integrated that dm from 0 to L. All right. So it's just basic math. I mean, not basic math, but it's math. All right. Should I go ahead? Let's find out tension now. Students, is it okay? All right. So I'll keep this acceleration aside. We're going to use that acceleration. Now, I'll again segment this into two parts.
Sir,
Yes,
your voice is breaking, sir.
voice is breaking. Others, is my voice breaking?
No, sir.
No, sir.
All right, all right. Please check your connection, or you can switch to YouTube. All right, if at all you have got network issues, you can switch to YouTube. All right. Okay. Now look at this. I'm sectioning it into two parts. Tension over here, action reaction pair. I told you, whenever you think of a force, any real force will have action reaction pair. So the moment I think of a force, I should think of its reaction as well. So here is tension, its reaction is on this part. So this is L naught minus X. This is X. So again, I'll use this part. I need to find tension. So T is equal to mass into acceleration. I know the acceleration, but I need to find the mass now. How will I find mass? T is equal to mass of L naught minus X, all right, ml minus X into acceleration is my tension. That's it. If I find out mass, I'm done. How will I find mass? Again, I'll do the same thing. I'll chop it into infinitesimal number of pieces, infinite number of infinitesimal pieces. I integrate this from X to L because I need to find only this mass. I don't need to find this mass. Before I have to find the whole mass, so I integrate this from 0 to L. But now I have to find only the mass of this part. I'll integrate this from X to L. So I'll have integral lambda naught into e power minus tau by L naught d tau from X to L. I'll get tension at a distance X times acceleration. Do you all understand this equation? Physics ends here. Okay, it's just math now. All right, I didn't draw the MAD. FBD and MAD both together will give me complete description of the diagram, description of the situation. So acceleration is A naught of both the parts. So T is equal to mass into acceleration is the physics of the problem. I'm applying Newton's second law over here. And next, I have to find mass. To find out mass, I integrate this from X to L because I need the mass of this part. I don't need the mass of this part. In total mass of 0 to L, I integrate from 0 to L to get the total mass. But I need only the mass of X to L, this part, which is of length L naught minus X. Length is L naught minus X. So I don't integrate from 0 to L naught minus X. I integrate this from X to L because this is at a distance X and this is at a distance L from the end, from where lambda is measured. All right. Can you now integrate this and tell me the answer? Is equal to lambda is constant e power minus t tau by L naught by minus 1 by L naught under limits x to L naught, sorry, into acceleration will give me tension. I remove this negative sign, I invert the limits L naught to x. So that becomes lambda naught L naught into e power minus tau by L naught under limits L naught to x into acceleration, where acceleration is f naught into e by lambda naught L naught into e minus 1. So lambda naught L naught gets cancelled out. Interestingly, so I substitute x first. So e power minus x by L naught minus 1 by e into f naught into e by e minus 1 is my tx. So then that becomes this is, yeah, check this step. If this is correct, I substitute x first, then I substitute L naught. When I substitute x, I'll get e power minus x by L naught minus, when I substitute L naught, I'll get 1 by e power minus 1, which is 1 by e. All right. So that's how the tension varies. So some constant times, this is constant, which is a naught. No, sorry, it's a constant times e power minus xl minus constant. So if we plot this function, is it okay? Is the math clear? So this procedure is very important. Okay, this procedure is going to chase us till the end of second year. All right, and there are many important questions, important in from the perspective of advanced and mains as well. Neat law, you'll have a simpler function. All right, you'll have x by L instead of having, or lambda by x instead of having e power x. You could have e power x as well, but you could have lambda by x as a function that I'll give you as a homework. All right, is the math clear? T is equal to m into a. Mass is what I have to find out, but mass of this L naught minus x part is what I have to find out. So which I integrate from x to L. All right, if at all I were to find out this mass, what would I do? I would integrate from 0 to x, would give me the mass of this part. But this part, I need to integrate from x to L naught. And total mass, to get the total mass, I integrate the initial mass from 0 to L naught. 0 to L naught for the total mass, 0 to x for this mass, x to L naught so for this mass. All right. So let's see, quickly plot this function roughly. I mean, let's sketch this function. So I've got some constant times e power minus x by L minus 1 by e. So e power minus x is this way, e power x is this way, e power minus x is this way. This is e power x. So I pull it down with some constant. E power minus x is, I know the function e power minus x. I pull it down with some constant, which is 1 by e into k naught. This is how the function graph goes. But tension cannot be negative. All right, it's always a pulling force. So if I consider this to be positive, tension is going to be pulling force always. So tension becomes 0 over here. Beyond this, there's no tension at all, because tension becomes 0 at this point, at x is equal to L. Look at this, at x is equal to L, what do we get? E power minus 1 minus e power minus 1, which is 0. So tension at x is equal to L is 0, and tension at t at x is equal to 0 is, tension at x is equal to 0, what would at x is equal to 0 be? 1 minus 1 by e by 1 minus 1 by e. So this gets cancelled out, I'll get tension as F naught. That makes complete sense. Tension at this point is F naught, tension at this point is 0. And in between, previous case, there was a linear variation, but now we have got an exponential variation. In the previous case, we had a linear variation like this when the lambda was constant, but lambda is not constant now, it's varying exponentially. So my tension is also varying exponentially, but decreasing from F naught, from 0 to L, exponentially from F naught to 0, between 0 to L. Is it clear, students? If you want me to repeat this procedure, I will repeat, but this is very important procedure.
Repeat, sir.
Okay, see, that's what. Before, you should have asked me before erasing it. Now that I've erased, I have to write it again. All right, look at this. All I'm doing is, I'm writing, is this equation clear? T is equal to mass into acceleration clear? For this mass, I write T is equal to mass into acceleration. Is it clear?
Yes, sir.
Now, next is I have to find out this mass. To find out mass, I'll chop this rope into infinitesimal pieces. infinite number of infinitesimal pieces. And in that infinitesimal piece, I'll write the mass as dm as lambda of tau d tau. D tau is the length. This is linear mass density. Mass per unit length into length will give me mass, which is dm. Now I integrate this from x to L naught because this is what I have to find out. Mass of this region I have to find out. So I integrate this from x to L naught and I get mass. Mass of what? Mass of L naught minus x length. Alright, so let's find out this mass. Substitute, plug this mass over here, you're done. Acceleration is known already. How do I get the acceleration? Force by total mass. To get the total mass, what do? I integrate it from 0 to L. But if I want a section of this section's mass, this one, let's say this is section A and section B. Section A's mass would be 0 to x. I integrate the same function from 0 to x. But if I want B's mass, I will integrate this from x to L naught. Alright? Is that clear? Is that point clear? Why am I integrating from x to L naught? Not from 0 to L naught minus x or
Yes,
0 to
sir.
x? Yeah, alright. Now, let's integrate that function. So lambda of x would be lambda naught into e power minus tau by L naught d tau. Integrating it from x to L naught is my mass. So that is lambda naught is constant. Integral of this is e power minus tau by L naught by minus 1 by L naught. I remove that minus sign and invert the limits L naught to x. Limits for x to L naught, I invert the limits L naught to x. Alright, this is purely mathematical operation. You cannot find physical significance of this. You may find, alright, if you find it, let me know. But all I'm doing is removing the negative sign and inverting the limits. So this would be lambda naught into L naught into e power minus tau by L naught from L naught to x. So I integrate this, I substitute the upper limit first. Lambda naught into L naught into e power minus x by L naught minus 1 by e. I got the mass now. I plug this mass in this equation. I'll get tension. So Tx is equal to lambda naught x L naught into e power minus x by L minus 1 by e into f naught by e minus 1 by e. Because a naught is f naught by into lambda naught L naught, sorry. This lambda naught L naught gets cancelled out. So what I now get is f naught by e minus 1 by e into e power minus x by L naught minus 1 by e. So I substitute x is equal to 0. That means at this end, common sense says the tension is going to be f naught. Let's see if my equation also tells the same thing. X is equal to 0, e power minus 1, e power minus 1 minus e power minus 1. Sorry, x is equal to 0 is what? Yeah, e power 1. So e minus 1 by e minus 1 by e. So this gets cancelled out. Tension is f naught. Tx is f naught. Makes sense. At x is equal to L, tension should be 0. So at x is equal to L, if I substitute L, e power minus 1 minus e power minus 1, 0, total tension is 0. So that also makes sense. And if I plot this function, intaku mundu it was linear, but this function is going to be exponential from f naught to 0, from between 0 to L naught. Is it now clear?
Yes, sir. Thank you.
All right, good. Okay, now as a homework, what you do is, what if I were to apply this force at this end? All right, find the tension as a function of x. Acceleration is going to be the same because I just removed this force here and applied here. F by m is acceleration. So acceleration is going to be the same. But I have to find out the tension as a function of x, where x is measured from this end. All right, so that's the question. I hope the question is clear. Force instead of over here, applied over here, it is applied from here. But my lambda is varying Look at this, students. It's not that easy. All right. It's a very good question. It's not that easy. It's mathematically a good question. My x is measured from here, but I want tension as a function of this distance. Let the distance be x, capital X. All right. But my lambda is measured from here. All right. So try that as homework. How will you write the integral? Just frame the integral. Integration, I'll do it for you. But you frame the integral. Do the physics part of the problem. Math part, I'll take care. Don't worry about the integration. Integration is very simple, just formula based as of now. All right. Now, I've got a same rope, all right? In which case, it is varying, lambda is varying like that from one end, and that rope is hung on a small nail, such that I'll just magnify this nail for convenience, so that this part of the rope, and there is some part over here. If lambda were constant, this is the nail. If lambda were constant, for this to be in equilibrium, that means for it to be at rest, if after I hang the rope like this, if I divide this rope into L by 2 and L by 2, then this would be in equilibrium. L by 2 equal ఉంటుంది, L by 2 equal ఉంటుంది, M by 2 equal ఉంటుంది, M by 2 equal ఉంటుంది. This will have no acceleration. Right? Acceleration will be 0. All right. Neat students, you try for lambda by x. Lambda is varying as lambda by x. You try for this function. All right. It is good if you can do this as well. All you have to do is frame the integral. Whether it is this function or this function, your integral depends only on lambda of x. Integral will involve lambda of x. Because integration, I'll do it. All right. So to frame the integral, you don't have to worry about the function. All you have to worry about is lambda of x, that variation of the function. But how it exactly varying, you don't have to worry. You will have to worry only when you have to integrate it. Integration, I'll do it. All right. So understand this one. If lambda were constant, half part is hanging this side and the half part is hanging this side, then this will be in equilibrium. If I disturb this equilibrium like this, it will start accelerating like this. This will come down with some acceleration, this will go up with some acceleration. But if lambda is not constant, that means it is thinner here, it's thicker here, then for that to be in equilibrium, my length also should not be same. Length will not be same, obviously. I'll just magnify this nail. All right. X is measured from here. So common sense will tell you that this length should be more than this length. If total length is, this length is x naught, this length will be L naught minus x naught. X naught will be less than L by 2 and L naught minus x will be obviously greater than L by 2 because it is thicker here and thinner here. So more mass over here, I mean thicker here and thinner here. So to compensate the mass, more length should be on this side and lesser length on this side because it's thicker. So more mass for the shorter length. More mass, I mean equal mass for the longer length. Obviously, common sense says that, right? So equation should also say the same thing. So I have to find out x naught, how much part should be hanging over here on the left side such that that should be in equilibrium. All right. Neglect this part because it's a small nail. Neglect this. I just magnified this to draw the diagram. It's just to represent the diagram clearly. All right, but it's a small nail on which there is a thread which is hanging over the nail. All right. So how do we do this? All I have to do is this. Mass on this part should be equal to mass on this part. That's what I have to do. Right? You all agree with that? Okay. All right. So mass on this part is how much? I chop this into infinite number of infinitesimal pieces. So at a distance of tau, okay, because I have to find out x naught, and this is x, variation of with x, I'll take x itself as my variable. So lambda of x dx, I integrate this from 0 to x naught, that should be equal to lambda of x dx from x naught to L. Do you all agree with this?
Yes,
Do you
sir.
understand this equation? Do you understand this equation?
Yes, sir.
Okay, Hasni understands. Gayatri, Shivani, Bhavna, other names I don't see. Do you all understand this equation?
Yes, sir.
Okay. Okay, good. So all I'm doing is equating this mass to this mass. And how did I find this mass? Integrating it from 0 to x naught. And how do I find this mass? I integrate from x naught to L naught. Right? That's what the total mass is, right? Okay, can I cancel this and lambda of x? I cannot cancel because that's inside the integral. Okay, now let's integrate this. So lambda naught into e power minus x by L naught dx, integrating it from 0 to x naught, is equal to lambda naught into e power minus x by L naught dx into integral x naught to L naught. Lambda naught gets cancelled out, so I'll erase this lambda naught. So integral of this is e power minus x by L naught by minus 1 by L naught under limits 0 to x naught, which is equal to same function again, e power minus x by L naught by minus 1 by L naught under limits x naught to L naught. This minus 1 by L naught and minus 1 by L naught gets cancelled out. I substitute the limits now. E power minus x naught by L naught minus 1. Because I substitute 0, e power 0 is 1. Should be equal to 1 by e minus e power minus x naught by L naught. All I have to find out is x naught now. So I'm done. 1 goes this side, e power minus x naught by L naught comes here. So I'll have 2 into e power minus x naught by L naught is equal to 1 by e plus 1. See, we are doing math, all right? Physics ended here. This is physics of the problem. Mass over here should be equal to mass over here, or mass into g should be equal to mass into g here. G anyway gets cancelled out, so that has gone. Once I get this, I can get x naught. Can you tell me what x naught is? I apply log on both sides and get x naught. Students followed?
Yes, sir.
Okay. Okay. If that is the case, let's. All right, I'll erase it. Any doubts? It's blurred. Yeah, any doubts?
No, sir.
Okay. All right. If that is the case, I'll give you a simple situation, simpler than this one, and help me do the problem. Help me solve the problem. Same function, lambda into e power minus x by L, but this time this is attached to a ceiling. Thicker here, thinner here. Lambda is varying from this side as a function of lambda into e power minus x by L. And this is at rest. All right. Required to find the tension at a distance capital X from here. All right. That's what required. Or at distance X itself, you say. I want tension as a function of X. How do I do this? I'll initiate the thought process. I cut it here and draw the FBD of the lower part. Why am I drawing thicker here? Because density is more here. Just to represent that density is more, I'm drawing thicker. So it could be different material at the same size, but I'm just drawing it to be thicker here to represent that X is starting from here and the lambda naught density is more here. And how much is density here? X is equal to 0. When I substitute X is equal to 0, I'm getting lambda naught. So density at this point is lambda naught. As I go away from this point, it's going decreasing with exponentially with X. All right. Now, if I section this at this point, this is my tension in the string, Tx, and this counterbalanced by mxg, where mx is mass of this part. So all I have to find out is mass of this part into g will give me tension. You all agree with this? See, FBD is complete. And what is the acceleration of the system? Zero. Acceleration of the mass is zero. So FBD is complete, MAD is complete. All I have to do is F is equal to MA. So net force is equal to 0. So Tx minus mxg is equal to 0. Tx is equal to mxg. All I have to find is mx. How do I find mx? At a distance of tau, I consider d tau. So lambda of tau d tau, I integrate this from 0 to x into g is my tension, Px, which is nothing but lambda of tau is lambda naught into e power minus tau by L naught d tau. I integrate this from 0 to x into g, mg, mx into g, mx. Here physics of the problem is ends here. Now this is just math. Right? Get used to it. Draw a fine line between physics of the problem and math of the problem. Physics of the problem ends here. FBD is done, MAD is done, acceleration is 0, so mass acceleration diagram is also drawn. Net force is Tx minus mg, which is equal to mass into acceleration, which is 0. So Tx is equal to mg. For it to be in equilibrium, Tx is equal to mg because it's in equilibrium. All I have to do is integrate this. How do I integrate this? Lambda naught is constant, g is constant. e power minus tau by L naught by minus 1 by L naught under limits 0 to x. But I remove this minus sign and I invert the limits. That becomes x to 0, which is equal to lambda naught g into L naught into 1 minus e power minus x by L naught. That's how my tension varies with x. Try plotting it. All right, as a homework, you plot it. Try plotting this function. How t varies with x. I got the function. All you have to do is plot the function. Sketch it. Sorry. All right. Any doubts here? Bhavna, Likita, Gayatri, Hashini, Shivani.
No, sir.
Okay, Hashini is very active today. Good. What happened to Gayatri, Bhavna, Shivani, Likita? No response. Are you all there?
Yes, sir.
Okay. All right. You want me to repeat anything? All right. Is there anything you want me to emphasize and do it again?
No, sir.
All right. Now, what if I invert the string like this? That means I hang it from here, thicker part here and thinner part here. I mean, let the thinner part hang and I this part this way. All right, it's not actually thicker here. I'm just showing it thicker. It could be thicker, but I'm just showing it thicker because to show that it's denser there. So what if this is the case? My x for the lambda is varying from here, but I want tension as a function of x from here. How do I do now? Think about this problem. So there are two problems you have to think about. One, I gave you homework before. Second problem is this one. First problem is when force is applied on the right, we have done. You have to do it when the force is applied at the left end. And lambda of x varies from this end, right end. In the first case, lambda of x varied from the end where the force was applied. But here, lambda is varying from the opposite end. But whereas force is applied to the left end. That's your homework. You just have to frame the integral. All right. If you're having difficulty in framing the integral, that means we need to work on it. We'll work on it. All right. Don't give up. All right. Things are going to be difficult, but tough will make you tougher. All right. Don't be afraid. Things are tough, becoming tough. Will I be able to cope up or not? No. All you need is no that determination that you can do it. The belief that you can do it. All right. Enough of motivation. Let's come back to the problem. All right. So how would the problem change? How would the equation change now? Think about this equation. We'll stop class here. I hope the problem is clear. Lambda ఇక్కడ నుంచి thicker function ఇక్కడ నుంచి vary అవుతుంది. But I have to find tension from this end. I have to find tension as a function of x from this end, which is capital X. ఇప్పుడు ఎలా చేస్తాము? How will I integrate? That's the only question. Limits vary అవుతాయి. All right. Limits will vary. Everything will be the same. You just frame the integral. Integration, I'll do it. Don't worry about the integration part. Frame the integral. Do the math, physics of the problem. Physics of the problem ends here. Right? This math, I'll do it. I'll help you do it. But you try understanding how to frame the integral for the problem. Framing the equation is very important. Once you get to know how to frame the equations, you are 99% done. That 1% math is very easy. With practice, you can get it. But getting the 99% requires thought process, deliberate thinking, deliberate practice. All right. So that is not that easy. but it is definitely doable, but not that easy. So why I've been saying that it's not easy, so that you sit and do the 10-minute exercise today. I presume you're doing it every day, so do it today as well. But today's exercise is not going to be simply thinking through. You will have to use pen and paper. All right. So students, do you all understand what I spoke today?
Yes, sir.
Okay. Only Hashini is responding. Bhavna, are you there? Gayatri is responding. Bhavna? Oh,
Sir,
yeah, Bhavna.
yes, sir.
Any problem? You're facing any problem?
Some network issues.
Okay. All right. So if you've got any doubts, please you can ask me in the next class, everyone.
Okay, sir.
Okay, sir.
All right. But do the 10 minutes exercise, which will require pen and paper this time. ఏం లేదు మనం చేసింది మనతో ఒకసారి చేయండి, థింక్ త్రూ ద హోల్ ప్రాసెస్ అండ్ ఆల్సో ట్రై టు ఫార్ములేట్ ద ఈక్వేషన్ ఫర్ ద హోంవర్క్. ఐఎమ్ జస్ట్ ఆస్కింగ్ యూ టు ఫార్ములేట్ ద ఈక్వేషన్, frame the integral. All right, do the physics part of the problem. Math part I'll take care. Thank you all students, have a great day.
Sir,
Bye everyone.
Thank you, sir.
chemistry notes, sir.